Hello WeatherTech students, our next set of videos coming this week, and today we're going to talk a little bit about satellite imagery, something that you've absolutely used at some point in your young meteorological careers, but we're going to take a little bit of time today to get into some more of the details behind what is a satellite, how do they work, and what can we glean from them. So again, the slides will be available on Top Hat. You can see the join code for my lecture here, 602987. For those in Professor Gobert's lecture, 393390. Again, that's 393390. And so go ahead and starting the presentation. Again, satellites here is what we're going to talk about today, and we're going to talk first and foremost about the different types of satellites. Again, some of what we're going to spend time on is talking about the different orbits, the types that are out there, and then the use of some of this imagery. We're going to talk about things, for instance, on how we can analyze jet streams and other troughs, ridges, other phenomena that we can sometimes get some information on through observational data, but we can get much more greater spatial resolution when we look at satellite data, since we're measuring things over a large area. And so satellite data has gone back now for about 60 years. We've been taking in some satellite data. And again, the couple types that we're going to spend with regard to the orbits here are going to be your GOES and your POES. Your GOES, your Geostationary Operational Environmental Satellites. These are going to be the ones that you're probably most used to using. The idea that they're going to be fixed above a certain point at the equator, and they're going to move at a speed that allows them to stay over the same spot on Earth's surface. And we refer to this as a geosynchronous orbit. As such, they are positioned up at around 36,000 kilometers, and so they are going to be at that height in order to move at a speed that will keep them again at the same point over Earth and encompass the from the poles across the entire globe, I should say, from the North Pole down to the South Pole. And this is going to be important because when it appears that the Earth is not moving underneath the satellite, we can then see what's going on with the actual weather systems. It makes it look as though the clouds are moving and that everything is behaving as we would experience weather at any point here on Earth's surface. And so relatively frequent observations can be taken, and we can start to see anything from the synoptic scale down to the mesoscale within this type of satellite imagery. The other type is going to be your POES, your polar orbiting satellite, oftentimes referred to as a LEO, or a low Earth orbiting satellite. And POES, since they are called polar satellites, are going to rotate around Earth's poles. And so they are going to do this in a way that allows them to stay in an area that is sunlit. They're going to revolve about 14 times per day around the Earth, and this means that through this revolution we're going to see 2 observations at most points with each polar orbiter. As a result of this rotation around the poles, we're going to keep these at a much lower altitude above Earth's surface, approximately 850 kilometers above Earth's surface. And these are going to be very useful not only for getting data at the poles, which is kind of on the edges of your GOES satellite, but it also is going to allow for some much greater resolution because we're closer down towards Earth's surface. And so again, looking a little bit about how these might appear, you got your geostationary orbit there going around the equator, and then your polar orbiter at a much lower altitude going around the poles. And obviously at times that's going to mean that it does go over the equatorial regions, and it's still going to give us a little greater resolution and a different glimpse into the weather even in those regions of the Earth. And so here we can see a little bit about the different satellites, looking at some of the geostationary programs. So we're going to spend a little time here now talking about GOES, and we're going to focus most of our efforts on the 2 in the middle there, GOES 16 and GOES 17. And so these are going to be what's known as GOES East, the one that you spend the most time working with because it's going to encompass the vast majority of the United States and give us the best geostationary view anywhere east of the Rockies. And then GOES 17, which is the GOES West and works more towards the western portion of the United States and out into the Pacific Ocean. You can see that we have some spares, so to speak, up there at GOES 14 and 15. In fact, we've recently had some discontinuance of certain spectrums on the GOES 15 as of March 2020. And then of course we always have some that are in the works. And so you can see here this calendar goes out to 2040 all the way on the right. Within your red rectangle we're looking at the current window showing where we have the GOES 16 and the 17 in an operational status. And so for instance, if we were to go ahead and toggle over to this image, you can go here on your own and feel free to click on things. And this, for instance, would show here again some of the supplemental operations ended on March 2nd of this year. It'll show you a little bit about the status of certain aspects of each satellite, let you know a little bit about the launch and operational dates, and stuff that you may find kind of interesting to dig into with some of your free time. And so if we toggle back to the slides, the link is down there in the bottom corner. Let's see if we can't get this to stop rotating over that portion. And so again, looking at GOES, this is, we've already mentioned, Earth oriented, staying over the same point, high spatial resolution over time and space. So the idea that we're looking at spatial, and we should say temporal resolution. One of the big changes over my lifetime as a meteorologist is how quickly we get imagery back, and we'll show an example on an upcoming slide of the capabilities of GOES 16 and 17 relative to its predecessors. Multispectral imaging, 16 channels. We'll talk shortly about what that means. In a nutshell, it means that we can look at a lot of different properties of what's known as emissivity. Different things are going to emit at different values, and so we can start to glean information on things like dust or fog or water vapor, whatever it is that we're trying to measure and get information on. And then again, a number of different soundings, different features that we can do with satellite information. And so here, going to the comparison here, your current GOES imager would have been the GOES 13-15 suite, so that is now the preceding GOES imager, and the future GOES R is actually now the operational GOES 16 and 17. So take column 1 here and say that this is in the past, and now column 2 is in the current, and then it gives you a little bit of information in the final column about some of the differences. And so I'm not going to go into every last detail on this slide because it would be cumbersome and take up more time and probably go beyond what most of you are looking to know, but the big takeaway is how much more we have both in terms of spectral coverage. So for instance here you can see that we've gone from 5 bands up to 16 bands, really enhancing especially some of our capabilities down here in the IR or the infrared spectrum. And here it shows a little bit in the right why we care. That's going to be one of the things that we're going to kind of just touch upon here, but I encourage you to take more time and really look at what types of things are available. For instance, fog at night, or looking at things such as snow and ice cover. May not be pertinent to everyday viewing of weather, but it might be something that if you do any type of research or have interest in certain aspects of the weather, may come in very handy. Resolution, much higher here again with the current suite of GOES imagery. And then if we look at coverage, here's one of the big things. Full Earth disks, previously every 3 hours, now every 15 minutes. CONUS, approximately every 15 minutes, now every 5 minutes. We can get mesoscale data, not available to every 30 seconds. And so this advanced baseline imager, this ABI, just allows for much greater temporal resolution. That's how we refer to that. And it's something that you all are used to because it's what you've used for most of your meteorological careers, but for many of us, this is something where we see the really neat, almost 1-minute imagery with some of our severe weather blowing up, which is just still absolutely fascinating to view. And so looking here a little more at GOES East, the one that we spend the most time on here, launched in 2016, and it's now been operational for over 2 years, well past its testing phase at this point. And so a lot of the statistics that are on this slide are things that we just briefly mentioned in the previous slide. The fact that it has so many more spectral bands, a couple that are down in the visible spectrum, more in the near IR spectrum, and then many in the long IR spectrum. 4 times better spatial resolution, 5 times faster temporal resolution. These are things that we may start to take for granted as this becomes what most people remember. But again, the idea that this is quite fascinating compared to its predecessor means that we can do a whole lot with it. And so the statistics and the information, the specs, I should say, that we talk here about the GOES 16 also go for the GOES West, launched in 2018. And so you can see the link on this slide for the full disk imager. If we take a moment and swap over, we can see some of the imagery that you might be able to notice here. So this is looking at one of the most fascinating things that came about with regard to the GOES 16, this geocolor, combining red and blue and kind of faking the green aspect of things a little bit to give us a really beautiful image of what's going on. And so I encourage you, take some time to just explore this website. You can even see sunset starting to come over the Atlantic. You can see our families of cyclones that we talked about with many of our journal articles. You can see this winter storm. This is being delivered to you from the preceding Thursday, so there's some winter storm warnings across the Dakotas. So you can see expansive cloud cover. And then you can start to look down in the southern hemisphere. Look at this different spin that we see. Pick out features maybe such as the intertropical convergence zone and other areas where, well, it looks like a pretty nice day over Florida. And so if you scroll back up to the top, we could, for instance, zoom in on things like the Great Lakes. If I do that right, it'll actually work next time. Let's go ahead and, for instance, just look down at Band 2, the visible in the red. Play around. You can loop these things for many, many hours. Take a look at what's going on. Well, we don't have a lot of information. Well, it's visible imagery, and so we can only get visible imagery during the day. And so you can see many things. You can see some stable layers out here in Pennsylvania with these ripples that look like fish scales. You can see some higher level clouds starting to spill ahead of the next system. Again, take some time and really look at this, and we'll spend some time in our next lecture at this as well. And so this is a great chart. I will stress to you that there is no need, repeat, no need for you to spend time studying this to the point of memorization, but it is a great reference and something that I strongly encourage all of you to read through and start to gain some level of familiarity, especially what we're looking at here in the couple of bands here, looking at the wavelength range as we work from these areas that are near the visible end of the spectrum into the near infrared and all the way out towards 12 plus microns, far into the long range version of the infrared spectrum. But what I want you to spend a little bit of time looking at is this sample use column. Why do we care? Why do we bother? Why is the fact that we have 16 versus 5 even important? And so you can see some of them are great for, say, daytime fog, but we wouldn't expect any use from a visible end of the spectrum for nighttime fog. And that may be where other ones, such as fog at night, are much more useful in this approximately 3.9 micron band. You can look even further and see things such as ozone, sea surface temperatures, other features that are quite interesting as you move further and further into the infrared portion of the spectrum. But you may be wondering, or maybe not, how do these satellites actually work? And so we have this idea of a passive remote sensor, an ABI, the Advanced Baseline Imager. And so here what we have is a number of different sensors on these satellites that are recording energy at these different wavelengths. And one thing to keep in mind, and we'll talk about this more when we talk about visible, is the idea that temperature is oftentimes going to be an important aspect into how much radiance is actually occurring. And so with all of these different sensors, we have little camera lenses. And these camera lenses are looking for something within a small range of the wavelengths. Again, possibly down in a small portion of the visible spectrum. You may have noted when I showed you the example a little bit ago, we actually looked at what was tagged as the red portion of the visible spectrum. We may, though, want to look at something, say, around 6.7 microns that's focusing more on helping us understand mid-level water vapor. And we'll spend some time in a future video looking at that with regard to jet stream imagery. And so here's, if we kind of put them all together and see what's out there, you'll notice that all 16 of these images are looking at the same time frame. You see clouds over all of these different things and generally speaking the same area, but we work our way from the upper left down here in the 0.4, 0.5 micron version of the visible spectrum Then we work our way here into the near infrared portion of the spectrum, and then all the way through the IR up to approximately 13 microns. And so looking at this, we don't really get a good feel for why we care about these in the moment, but an idea of what the different images look like. And we will also talk about how we can do different enhancements to these to be able to bring out the features that we are looking for. And again, what we'll conclude this lecture on is the idea of the electromagnetic spectrum. And we'll spend some time starting the next lecture with this as well. There's a number of things here that do absorption, or that I should rephrase that absorb this radiation effectively. And so we know, for instance, as we get down to the ultraviolet portion of the spectrum, well, oxygen and ozone are very, very important and absorb the vast majority of that incoming UV radiation. However, we have our solar window, which lets through the visible portion well. So here we can see, for instance, the red portion is visible. What's being reflected outward from the Earth and being noted by our satellite. We have a portion here in the IR. You'll notice here that we have some mid-level water vapor here, channel 9, around this 5, 6, 7 micron portion, where, well, water is doing a really good job of absorbing radiation. So we'll talk about that when we talk about water vapor imagery soon. Another atmospheric window here. So channel 14, classic IR, around 11.2 micron. Again, a portion where a large percentage is able to make it through out to the satellite. And so that will conclude this first lecture. We'll talk again shortly about the different types, visible, infrared, and water vapor, and explain a little bit more then about why we care in terms of features such as jet streams, troughs, and ridges. Take care. Talk to you again soon.